let's make a few changes. So I just ran it again. To go forward to get a fair basis of comparison, I think we want to start using like random states. So if you go in here and you put in the parameter, say like random state equals, and you put in 2, I just pick 2 sometimes for base 2. You can put any number. And then let's see if I do this twice. I should get the same score twice. I'll actually may need to do with cross-file score again. So let's check that. Get a 657.689. And a different one. I think you can often put in random states. So let's try it here as well. Let's try it again. Okay, so it doesn't take random state. Yeah, there are like little issues with getting the same score here. Let's try to set it here. Okay, random state equals 2. So I run the k fold. Now let's try to run this. And get 673.96 and 673.96. Yeah, so it looks like when it's calling k-fold, it's like redoing it. Okay, so the only reason why I'm doing this, not because, oh, that's the right score, is just to get basis of comparisons when we're doing the grid search. That way, you know if there's an improvement that's because of the new hyperparameter, not because of some new randomization in the random forest regressor. The other thing is that I feel like this is too much. So you can round these. If you do dot round, comma 2, sorry, parentheses 2. This is the style for NumPy arrays, just dot. If you weren't sure, you could be like, well, it's showing it there because I just used it. Dot round 2. Okay. This can round it to 2 decimal places. It just makes it cleaner. And so now when I run it, I don't know, just more readable, basically. Okay, so again, the 2 changes were put in random state equals 2 here and random state equals 2 here with the k-fold, okay? This is allowing us, and what's kind of interesting is your score should then match mine, okay? It's allowing us to establish, consistent scores for a basis of comparison. Now, let's start with a grid search. So let's do a new text header, grid search, or fine tune. We'll just say fine tune. Fine tune RF. And after I put one here, then I can go back to the top and add another one too. And I'm going to do a new text header and call this one, I don't know, I guess first RF model. And put it at the top. Okay, I usually do the second one after the first because I don't know like when I'm going to stop. Maybe I'm just loading the data here, but we went ahead and built a model. And again, I can, of course, hide it and then go down to fine-tuning the random forest. All right, so how do I do that? I'm going to go ahead and just do it. We've done this before, so I'm going to try to do it not relatively quickly. We're going to build a new grid search function, okay? So from sklearn dot model selection, I'm going to import grid search CV and random forest. I thought it was capital somehow. There it is, grid search CV and randomized search CV. Okay. And now we're going to define a function. Let's call it grid search. I kind of just want to use the function we did last time, but we can just do it again because sometimes you're going to want to make some changes, but there's also something to be said about not using the same code. How should I say that? There's value in copying your code, okay, not mine, your code. So if you did the last video with me, you should be able to find it. Like if you just go to collab.research.google.com And then if you scroll down, you should see the last one that you made, which looks like, wow, maybe we didn't do a grid search there. Maybe it was back, it looks like in decision tree tuned, okay? So back in decision tree tuned, right, I can pull that up. This is code that we wrote together in this class. And I can say, where is my function? Here it is. Here's the function here. And note that we have some nice piece to it because we could set random equals false and the number of like iterations or the number of combinations. And it's all here. Okay. And it's, it's kind of a clean function. In fact, I think I'm going to copy it. Okay. So Command A, Command C, and then make a couple of adjustments. All right. So let's just put it all in here and go over it. So I've got a grid search function, it takes parameters. By default, random is false. The number of combinations. Now this one's a little, I'm going to change it to 15. Okay. You could call it what they call it, number of iteration in iters. Okay. Number of iterations. And put the imports in here. Set grid of parameters. We're just copying that. I'm not sure. I guess we're redefining it. Now the model here is not a decision tree classifier, right? This is where you need to adjust your models. This is a random forest regressor, okay? And we decided we are going to have random state equals 2, right? Then when we do the grid search CV, scoring is not accuracy, okay? Scoring is negative mean squared error, and CV will be k-fold. So the point is you want to change these, okay? And if random, then we invoke the randomized search CV. So that's a separate thing, and we need to match that. So k-fold, and in iter equals, I just like to name it the same thing, maybe in iter. Number of iterations instead of combos. Okay. In iter. My notebook will be copied so you can check it out if you're getting a little lost here. And then you just fit it to the data, and then we return the best parameters and the best score. So it's kind of a clean function. It's much cleaner than the one I did for the book, I can tell you. I think it looks good. Oh, no. One last thing. The scoring, right? We don't want the negative mean squared error. We want so we want to change the scores. Okay? So how can we do that? Just say get RMSE. Do it like this. So RMSE equals, see where it says grid best score? Okay. Copy that. And so that's one number, right? So we want to take the negative of that. And then, just for clarity, then that's all to the 1/2 power to the 0.5. So you have to go through that extra step, but then that's what we want to return is the RMSE. Okay. Is it doing the mean by average? Maybe. Let's see if this is working. Okay, so let me just go over it with you one more time. Okay, this is our function to run a grid search, right? It's going to have a grid, a dictionary of parameters. It's not randomized by default, okay? And this initer is for when it is randomized, actually. It says, hey, we'll just pick the 15 best combinations. Get our imports in, that way this function stands alone. Parameters equals parameters. Initialize the random forest. By the way, something you'll see in the book is in jobs, and it can equal -1. And what that does is it allows you to take advantage of parallel processing if it's there, available to you. So it can't hurt you. It can only help you. That's just a little fun FYI. And -1 means as many as possible. Okay, no limit. And then here's our model. It's the grid search. We put in the random forest. We put in the parameters. We're going to use the negative mean squared error scoring. And CV is the previously defined k-fold. Okay, just 5 folds. Now, the only difference is, hey, if it's random, instead of grid search, we use randomized search CV. Oh, I didn't. I said everything else should match. I see I did not change the scoring. Okay, the scoring needs to match. Okay, so that's why it's also good to check code, and you put in a big chunk of code there. Yep, and it also, we can add this. We upped it from 10, so it potentially is better. Gives us more combos because it's 739 rows. We can get away with 15, I think. We'll see. Then you fit it to the data, and then we extract the root mean squared error score, and we show that along with whatever was the best parameter that gave us that. Okay. So again, let's be clear about what this does. What it does is, let's run it first, make sure it works, and we'll talk about what it does with code. So let's set up the parameters. Okay. So let's use, this is just to test that it works, and we can talk about what it does. Let's use something we've done a lot with, which is max depth, right? Like how many branches of the tree do we have? And for dictionary, it's colon syntax, and then it's going to be a list. And so the max depth could be, you can have 1, that is called a stump. It's the smallest possible one. 2, 4, I sometimes just go double them, like, yeah, I don't know, 6 could be good, 8, 10. We can also check out none. I think none is the default, right? And that there's no limit. So that's a reasonable start. And now I want to call the function. So to call it, I type in grid search, and I just put in the parameters. Okay. Now what this is going to do, it is going to create. Let's see if that syntax is correct. Might take a little time here. What this does is it's building a random forest for each of these different max depths. Okay. And note the reason why it's taking some time here is because it's doing, interesting. Okay, so it's interesting because it's none. It's doing like it tried it with 1. What's max depth? 1 level, only 1 split in the data. Tried it with 2, tried it with 4, tried it with 6, tried it with 8, tried it with 10. Now each time it tries it, okay, like look at, say, the 8. What is it doing? It's building each random forest builds 100 decision trees that only have 8 splits. So it's got a max depth of 8. Okay. It says max depth because I guess if it was perfectly split at 4, you would stop. Typically it's not. So it builds, so that's 100 decision trees, right? That's 1 model. Okay. We've talked about this before, right? Because how it can really go up in scope. Don't you know what the code does? The code gets scores. It checks the mean scores for each of these, okay? So for each random forest. And it gets them from doing the 5-fold split. And it found the best score with a max depth of none. And note that that's, it's not exactly the same for whatever reasons, but it's pretty comparable to the original score. Okay? Now, I'm going to run it again because I want to see it. Does it actually give the same score? Like I want it to, but will it? I don't know. Oh, and I could have modified it too to see. Maybe you get better with like 12 or 14 because, you know, we know with none, like there's a good chance that it is overfitting. Okay? Because then each decision tree goes pretty deep. It does give the same score. Great. So what I can say is, well, hey, if those don't beat none, what if I go higher and try like 12, 14, 16, 18, and 20, right? Like, go ahead, press Shift Enter. You can put in your own numbers. The idea is that you would think that bottomless trees probably aren't going to ultimately be the best. There's probably some other combination that's going to be better. Now, this will take also longer because note that a depth of, well, there's 16 is going to take longer to build, of course, than a depth of 2. And you can see that we were able to beat the score, okay, using 16. Okay, So it looks like the function is working fine. And now I just want to jump in and use like a big one. Okay. And then we can talk next about the individual hyperparameters. I say that, however, I haven't done in estimators yet. I really wanted to do in estimators. So before that, here's what I'm going to do. Copy this. And oh, by the way, note that we could also get the rounding here if you like. Maybe it'll work if it's a number. I think at this point it's just a number, right? Because they're just delivering a number here. So if it's a number, then you can just do like the traditional Python round RMSE2. Find out. So you just got to try things. Note that's different than the dot round, which is like for NumPy arrays. Let's run it again. Okay, so I know I got the best results so far with 16, but it's also interesting, and I can just use that instead of none because that's a little better. But it's also interesting just to look at this in conjunction with in estimators. Okay, so in estimators is the number of trees, right? So by default it gives 100. We can say, well, is it going to give better with like 50 less trees? We know what it gives with 100, but you know, I guess you could just still put it in there. It's really a waste because you have the score above, so it's not. Try 200 and 400. And is it the case that simply more is better, right? Now this is 800 trees is a lot, but it's only going to build 4 because the total number of models, we count random forest as one model, is each one of these with a 16, so it's a times 4. Okay, so I sometimes treat in estimators separately because in some sense, like the more trees, like per random forest, the better the model, but it's not strictly the case. I mean, you can certainly start to overfit. We'll see if it can beat 673. You know, I frankly don't know. You can see it is taking some time, right? Because even though in this case you've got 1, 2, 3, say these 4, each have 100, whereas this one is 800. And note that we did get a little higher, a little better score. Not a lot better though, with 670.46. I say that because, you know, you've got to really start to interpret results. It's a big part of machine learning. And what do I mean by that? Here's what I mean. This model that got the best score has 4 times as many trees, right? It goes from 100 to 400. And the gain is only like 3 points. So is it actually worth it? Maybe not, because it actually takes more time to build. Now we'll come back to in estimators though at the end. I'm going to give it a pause for now and just stick with 100. By comparison, in this case, I could argue, hey, well, yay, you know, max depth of 16 only got like 6 points better, like 6 rentals better than the none. Is that worth it? Well, absolutely, because you just made a model that is faster. Instead of bottomless trees that take longer to build, you set a maximum of 16. I think that's probably a little high and we can change it. Okay, so what we're going to do is we are now going to search to a randomized setup. And I'm going to get it from the GitHub page for this class. So if you have this up, if you go to the raw data and you go back to the the folder for this chapter, you see this random forest bagging.ipynb. IPYNB stands for IPython Notebook. I tend to look at these before I do these live sessions. Typically these have more code because there's more contained there. Although I'm doing things kind of, I've learned more since I've written this, and I've learned that it makes sense to go ahead and shuffle kfold, which I didn't do here. But if I scroll down to the bottom, you'll see right here, a nice, like a randomized search grid. And I'm going to copy it and make a few adjustments. Or maybe not, maybe I'll just copy it. See the parameters here? Okay, so I'm going to copy that in. I'll try to put this link up. If you can't find it, I always have the links to the notebook up, so you can always look inside of my notebook to get it if you don't have it. I like to show people how to find things, which I mention a lot, because you don't want to rely on me personally, like what I tell you for the code. You want to know where online you can go to get code. This stuff will always be here, most likely. So this is just like a start. And I don't want to put like a lot of emphasis. I'm going to try to move it so you can see it better. I don't want to put a lot of emphasis on it, like the initial numbers right now, because the reality is that you can kind of start with anything, okay? And I do want to put emphasis on what some of these are that we haven't seen. That was a mistake to go all the way down. By the way, if this is because I'm copying and pasting, if you actually do it, write it on your own, it won't. It'll set the spacing nicely. All right. I'll leave that. So this is a big one. Now, if I look at the code before, I just do grid search, but, and this might take a little time, so I may pause the video. Now, okay, I do want to, of course, keep the new parameters in, but you see random, now I won't definitely need random equals true. This code will not finish if you don't do that. Why not? Because in effect, you see all the lengths of these lists, you're multiplying them all together. So this is like 1, 2, 3, 4, 5, 6. Are they're like, and then this is how many, wait, is it times? It's not even times, it's like greater than that. It's way too much. Okay. Is it times? I guess it is times. But it just gets too big. Okay. So I'll run that and we'll see how long it takes. It's going to run 15 decision trees. I'm not changing in estimators. Maybe I can wait because actually it's only like 100 decision trees each time. So, I mean, I say only, that's right. How many decision trees is that? Well, that's 1,500. But then it's also cross validation. So that's times 5. So this is building 7,500 decision trees. You can see it was actually relatively fast. Now let's see. I'm very curious to see what score we got. Interesting. So we did not get a better score, right? We got 720. And something else that's interesting about this is you can kind of like use what you have. So you don't ever have to like go back and start afresh. It's like we obtained information and we got that 16 was the best max depth. And so maybe we're going to see if I change it to 16, right? Then I'm potentially starting with the best. And I'm just saying, hey, can I change some of these other values to get a better score? So I'm going to try that. That might take a little longer. Okay. And what I'm really looking for is to see if I can get a better starting place than this 673. I mean, 670 with the in estimators going up. Okay. And so what we're going to do for the final segment of this lesson is we're going to talk about some of these different hyperparameters. Okay. Oh, just about to cut it off. It says up here by the 27 seconds. There it goes. We didn't improve it. Okay. So we'll work on this.